So the next speaker is Jayakrishnan Madathil, who will talk to us about temporal triadic closure. Off you go.
Thank you for the invitation. I'm sorry I couldn't be there in person. So here we go. You can ignore the title. So what I'm going to tell you about is something called temporal C-closed graphs. And just to be sure, this is the temporal graph model that we are talking about. You have already seen it. The vertex set remains the same. The edge set changes over discrete time steps. And you can also formalize this as a graph G, a static graph G, and a function lambda that assigns to each edge a set of time steps at which that particular edge is active. One point, we are talking about graphs, temporal graphs with finite lifetime. So the time goes from time step t equals 1 to time step t equals capital T. All right, so this is the model that we are going to talk about. So if you ended up in this room by accident, then this is the picture that I would like you to remember. There is a graph involved, and then there is time involved. Okay, and the stuff that I would like to talk to you about falls under the broad objective of translating ideas and concepts and algorithms from graph literature to temporal graphs. Okay, so if you have a theorem, a hypothetical theorem about graphs, it says something about graphs, say theorem 1 in this case, then it is quite natural to ask, hey, can we prove a temporal analog of this theorem? So this is the prototypical goal, or the prototypical objective, the idea behind this whole project. And this is particularly relevant in the context of algorithm design because, as you know, any number of graph problems are NP hard, even for static graphs, but many of them do admit algorithms when the graph satisfies some nice structural properties, often characterized by a structural parameter or a graph invariant, as they are called. So many problems may not have a polynomial time algorithm, n is the number of vertices of the graph, but may admit algorithms with this kind of running time, f of p times polynomial in n, where p is some graph invariant. Some of the more common invariants are things like tree width or degeneracy, etc., etc. And over the last few years, there has been some interest in trying to define graph invariants or structural parameters for temporal graphs that can then be exploited to design algorithms with this kind of running time. So this is the theme behind the talk. Okay, and in recent years, for example, there have been multiple attempts to define tree width of a temporal graph or neighborhood diversity, click width, etc., etc. And the invariant or the parameter that I would like to tell you about is something that was inspired by social networks, particularly the so-called triadic closure property exhibited by many social networks. So many social networks have this property that if there are three nodes, U, V, and W, and U and V are adjacent to W, then it is quite likely that U and V are adjacent to each other. So this structure, these three nodes with these two connections, that's what's called a triad. And if U and V are adjacent to each other, then we say that the triad is closed. Or in lay terms, friends of friends tend to be friends themselves. And the object that I would like to talk to you about is something called C-closed temporal graphs. So for that purpose, it needs some context. And for that purpose, I am going to ask you to ignore this one word temporal, the most important word in today's proceedings, for the next 5 minutes. And I am going to talk about static graphs, particularly C-closed graphs. And I am going to evangelize C-closed graphs for the next 5 minutes. So please be patient. So C is a non-negative, is a positive integer. And we say that a graph, a static graph, is C-closed if it satisfies the following property. Take any two vertices U and V with at least C many common neighbors. If they are adjacent to, so take two vertices U and V. If they have at least C many common neighbors, then U and V are adjacent to each other. If that happens for every pair of vertices, then we say that the graph is C-closed. So if you are someone who uses a platform like Facebook, then you would know that if you and I are on Facebook and you and I have a lot of common friends, then it's likely that you and I would be friends with each other. So this is an abstraction, a formalism of that property. And the closure number of a graph is the minimum C for which it is C-closed. So you can see that closure number is exactly this quantity. So look at any two vertices U and V that do not have an edge, and look at the common neighborhood of those two vertices U and V. So U and V are not adjacent to each other, which means they can have at most C minus 1 neighbors in common. So plus 1. So go over all pairs of vertices U and V that are not adjacent. Look at the size of their common neighborhood, add 1. That's the closure number of a graph. So the 0 is there because it may happen that the graph is a clique and there are no two vertices that are not adjacent. So to deal with that case, we add this 0 here. So this is the closure number of a graph. Just to give you some intuition or some idea about how closure number compares with other parameters, as you can see, closure number can be at most 1 plus maximum degree of the graph, because the size of the common neighborhood of any two vertices cannot exceed the maximum degree. So closure number is at most 1 plus maximum degree. But you can see that this is completely incomparable with many other graph parameters like tree width and degeneracy. Look at these two examples. On the left, you have a complete graph, a clique. It has, say, let's say it has n vertices, then it has order n square edges. Its tree width is large, degeneracy is large, max degree is large, but closure number is small, because take any two vertices, they have a common neighbor, but they're also adjacent to each other. So the graph is one closed. A complete graph is one closed. On the other hand, here on the right side, you have a biclique. It has two vertices in one of the sets and n minus 2 vertices in the other set. So it has a linear number of edges, small tree width, small degeneracy, large max degree, and large closure number. Because these two vertices in the top set, they have n minus 2 common neighbors, but they are not adjacent to each other. So closure number is n minus 2 plus 1, n minus 1. So as you can see, closure number of a graph is incomparable with many of the other commonly studied graph parameters. And closure number, or C-closed graphs, were introduced by Jacob Fox and a couple of his co-authors in 2018. What they showed was that a C-closed graph with n vertices has at most this many maximal cliques, 3 to the power c over 3 times n square many maximal cliques. So if we did not have this property on arbitrary n-vertex graphs, the number of maximal cliques could be as large as 3 to the power n over 3, exponential in n. This was followed by this work in ESA 2020 and a series of papers after that, which showed, so the authors of this paper argued that, look, closure number is a very useful structural parameter for graphs, because it's quite easy to understand, it's polynomial time computable, and they also showed that, it has reasonable values, reasonably small values on a handful of real-world networks. As I said, as we saw, it's incomparable with many other commonly studied graph parameters. On top of all of that, a number of problems admit efficient algorithms, FPT algorithms or XP algorithms, etc., on the class of C-closed graphs. So it's extremely useful for the purpose of algorithm design. And there has been maybe more than half a dozen papers on various algorithmic problems on C-closed graphs since 2020. So this was a table from the original paper that introduced C-closed graphs. They looked at a bunch of real-world networks and computed the C value, the closure number of a bunch of real-world networks. So n is the number of vertices, m is the number of edges, and c is the closure number. You can ignore the last column, weak c. So as you can see, even for very large networks, c is reasonably small. This was in the 2018 paper that introduced C-closed graphs. They also computed this quantity called cumulative closure rate for a particular real-world network, the Enron email network with thousands of nodes and edges. So what is on the x-axis, what you see is the independent variable, the number of common neighbors. On the y-axis, what you see is what's called the cumulative closure rate. It is the number of pairs of vertices U and V with at least x many common neighbors, and the vertices U and V are adjacent. There is an edge between U and V in the graph. 2, in the denominator, what you have is the number of pairs of vertices with at least x common neighbors. So take any point xy, it describes this value, gives this value. So as you can see, the y-axis goes from 0 to 1, and as the number of common neighbors increases, the y value goes to 1. If we have time, I'll show you a temporal analog of this plot. Okay, so that was all about C-closed static graphs. Now we are going to define C-closed temporal graphs. So the big question is, how do we define C-closed temporal graphs? What would be an appropriate temporal analog of closure number? Second question is, can we prove? I told you, closure number has been extremely useful for algorithm design. So can we prove similar algorithmic results on C-closed temporal graphs? Okay, so once again, recall, this was the picture that we had, the temporal graph model, just a bit of bookkeeping, a matter of terminology. So we would be looking at intervals of time. Say, for example, this blue rectangle on this time axis. Say the left endpoint is A, the right endpoint is B, and this is a time interval. And we say that two vertices U and V are adjacent during this interval AB if this edge UV is present at some time step within this interval. The edge doesn't have to be present throughout the interval. At some time step is good enough for us. If that happens, then we say that the vertices U and V are adjacent during AB. Similarly, we say that W, vertex W, is a common neighbor of U and V during this interval AB if this edge UW is active at some time step and this edge VW is active at some time step during this interval. Okay, so UW and VW need not be present at the same time, as long as they are present as long as each one is present at some time step in this interval, then we are happy. If that happens, then we say that W is a common neighbor of U and V. Okay, so here is what we did for C-closed temporal graphs. We came up with a definition of a temporal C-closed graphs, again with this triadic closure property of social networks in mind. So this is how we define. So this is an informal definition. What we said was, if look at two vertices U and V, if they have at least C common neighbors during a short interval of time. So this deep blue interval, look at this deep blue interval, okay? Take any two vertices, and if they have at least C common neighbors during any short interval of time, then they should be adjacent to each other around that time. So this, if U and V have at least C common neighbors during this deep blue interval, then they should be adjacent to each other in this pale blue interval, during this pale blue interval. If this happens for any two vertices and all intervals, then we say that the graph is temporally C-closed. So the formal definition will quantify this short interval of time and around that time and all that, okay? And with this definition, we showed that, we can in fact use this for algorithm design purposes. So the first thing that we showed was that we showed an upper bound for the number of maximal temporal clicks. I haven't defined what I mean by a temporal click, but you already saw a couple of definitions today. So what we showed was that if you look at any temporal C-closed graph with n vertices and lifetime capital T, then it has at most this many maximal clicks. So an exponential factor in C, 2 to the power order C, then a polynomial in n, the number of vertices, n square multiplied by the lifetime. Okay, provided the graph evolves slowly. I haven't defined this yet. We'll come to that in a bit. Okay, so if the graph is C-closed and it evolves slowly, then the number of maximal clicks is bounded. If we did not have one of these properties, okay, either C-closed property is not there or slow evolution is not there, if either of those happens, then the number of maximal clicks could be as large as 2 to the power omega of n, exponential in n times t. We also showed that this bound can be turned into an algorithm that enumerates all maximal clicks. Okay, again, in time proportional to the number of, with a polynomial overhead. We also showed that then we extended this result in a couple of ways. One extension was we looked at generalizations of cliques. That was one thing. Then we also defined a weak notion of C closure. I don't think I'll have time to go into the details of that. There was a weak C closure defined for static graphs as well. So we adapted that into the temporal setting. So for weak C closed graphs also, we showed a similar bound and similar algorithm. So that was for the theoretical part. We also looked at a handful of real world networks and just computed the C value for a bunch of really small networks, and it looks promising. That's all I can say about the empirical stuff at the moment, because we didn't do any extensive analysis. Okay, so on to the slightly more technical stuff. So this is what I said the definition was. If two vertices U and V have at least C common neighbors during a short interval of time, then they are adjacent to each other around that time. So the formal definition is merely a quantification of the blue stuff. Okay, what do we mean by short interval? What do we mean by around that time? So to do that, we use these three numerical stuff: delta naught, delta 1, delta 2, three numerical quantities, all non-negative integers. So the formal definition, almost formal definition, is like this: for any two, look at any two distinct vertices U and V, and look at any time interval AB. AB has to be sufficiently short, which means B minus A has to be upper bounded by delta 1 for any U and V and for any AB with these properties. If U and V have at least C common neighbors during this interval AB, so that's a deep blue interval AB, then U and V are adjacent to each other during A minus delta naught and B plus delta 2. So you go delta naught steps to the left and go delta 2 steps to the right, you get the pale blue interval. So this edge UV should be present somewhere in this pale blue interval if U and V have at least C common neighbors in the deep blue interval. So this is the almost formal definition. And now, as I said, our objective is to bound the number of cliques, and for that purpose, we do need a definition of temporal cliques, and we borrowed a definition that was already there in the literature. So it's called delta clique. Delta again is a number. So there are so many parameters going around here. So delta again is a non-negative integer, and so what's a clique in a static graph? A clique is a subset of vertices, so that between any two vertices there is an edge, right? So a clique in a temporal graph is a pair of things. X is a subset of vertices, and PQ is a time interval. Okay, so we say that this pair is a temporal clique if the following thing happens. Look at any two vertices in X, little x and little y, and look at any time interval of length delta. So start at any time t and end at time t plus delta within this interval PQ. Then for any such delta long window, this edge xy should be active during that delta long window. If this happens for every two vertices and every time interval t plus delta within this interval PQ, then we say that this pair is a temporal delta clique. Of course, then we need to define what we mean by maximal delta clique. By maximality, we mean that we should not be able to add any more vertices to X or extend this interval PQ while still retaining the delta clique property. Okay, so this is what we mean by a maximal delta clique. So the number of maximal delta cliques could be as large as 2 to the power n times t. The n is the number of vertices and t is the lifetime. So the question is, can we bound the number of maximal delta cliques by this kind of a function, f of c. C is the C closure number of the graph, again with respect to delta naught, delta 1 and delta 2 times polynomial in n times lifetime. So what we showed was that yes, if the graph evolves slowly, then we can do this, otherwise we can't. So let me give you an example of a temporal graph. It is C closed. In fact, it will be temporally 1 closed, and it has an exponential number of exponential in n many maximal delta clicks. So the graph construction is fairly simple. The graph has n vertices. Look at all the vertex subsets with at least 2 vertices, okay? So exclude the empty set and the n singletons. So you have this many subsets of vertices of size at least 2, x1, x2, up to so and so. So for each xi, you choose a time step ti. So you choose an increasing sequence of time steps. The only thing is that these time steps should be sufficiently far apart. You can fix your delta, okay? Fix any delta. So these time steps should be sufficiently far apart. Then what are the edges? So at time step ti, all the edges with both endpoints in xi are active. Okay, so if you can think of a timeline, then it's like if you think of a timeline and at time ti, all these edges within xi becomes active. It's not difficult to see that this graph would be temporally one closed for any choice of delta naught, delta 1, and delta 2. And each of these things, xi, comma ti minus delta ti plus delta, would be a maximal delta click also. So you have an exponential number of maximal delta clicks in this case, even though the graph is temporally one closed. And it's not difficult to see that why this happens. It's because you have all these edges appearing in xi all of a sudden, then they disappear at the next time step. So the graph changes, or the adjacencies changes too much and too quickly. So in the next step, we are going to limit this behavior. And I should add that this is not a particularly satisfying example because the lifetime of the graph is also exponential in n here. But again, it's not very difficult to construct other examples where this doesn't happen. So even for a constant delta, you can build temporal graphs with exponential in n many maximal delta clicks. Okay. All right. So we don't want the graph to evolve very quickly. We want it to evolve quite slowly. And it's this idea that led to this definition of an eta unstable graph. Eta, again, is a numerical value, a non-negative integer. We say that a graph is eta unstable if this happens. Between any 2 consecutive time steps, the neighborhood of each vertex changes by at most eta. So look at time step t and time step t plus 1. Nt of v is the neighborhood of the vertex v at time step t. Similarly, nt plus 1v is the neighborhood of vertex v at time step t plus 1. So this difference, the new vertices, or rather so what happens in the transition between time step t and t plus 1? V loses some neighbors and v gains some neighbors. So the number of neighbors that vertex v loses is at most eta. Number of new neighbors that vertex v gains is also at most eta. If this happens, then we say that the graph is eta unstable. Okay, if the graph is 0 unstable, then eta equals 0, then no change happens. So the graph is essentially a static graph. Okay, so this is what we mean by slow evolution. So what we showed was that if the graph evolves slowly and temporally C closed, then it has at most this many maximal clicks. So how this works, so here is a 60-second proof outline. How this works is as follows. We associate every maximal delta click in the graph with a tuple of 3 different objects. We have the tuple consists of a pair of vertices u and v, a time step t, and a subset of the common neighborhood of u and v during this interval t comma t plus delta, such that uv, so the edge is not active at any time step within this interval. So if you look at this picture, you have look at the pale blue interval, t and t plus delta, with endpoints t and t plus delta. You skip the first delta naught time steps. So look at t plus delta naught, and then you go delta 1 time steps further to the right. So you get the deep blue interval. So the argument is something like this. This edge uv is not active. This edge uv is not active at any time step in this long interval. So you look at this middle portion, the deep blue interval. It can have at most c minus 1 common neighbors. U and v can have at most c minus 1 common neighbors during this short interval, the deep blue interval. Why? Because the graph is temporally C-closed. If U and V had more than C common neighbors, then U and V would have to be adjacent sometime during this long interval. So that doesn't happen, which means within the short interval, U and V have at most C-1 common neighbors. Now the graph evolves slowly. So at each time step, in the pale blue interval, each U and V gain at most at most h many common neighbors. Okay, so C-1 plus delta is the length of the interval. At each time step, U gains at most h many common neighbors, and V gains at most h many common neighbors, so altogether twice h many common neighbors. So the subset of the common neighborhood can have at most size at most this C-1 plus twice eta times delta. So the size of the common neighborhood is this much. Therefore, the number of subsets of the common neighborhood is 2 to the power this quantity. So as you can see, we have a pair of vertices U and V. They have at most n square many choices, a time step t, which can have capital T many choices, and the subset can have this many choices. And for the combination of these three things, we show that there is at most one maximal delta click. So hence the total number of maximal delta clicks is also bounded. This is the overall argument. All right. Okay, so a quick look at the empirical results. So as I said, we looked at just a few real-world networks. With the largest network that we looked at had 217 nodes, and the one conclusion is that if you look at all these networks as purely static graphs, okay, so ignore the time, just treat them as static graphs, compute the closure number of those networks. It is quite bigger than if you treated them as temporal graphs and computed the temporal C value. So the temporal C value is actually smaller than the corresponding static thing. This was one thing that we looked at. And yeah, so here is the plot that I promised you. It is so this is a contact network in a hospital, I believe, in France. And what you see is on the x-axis is the number of common neighbors. On the y-axis is the cumulative closure rate. So what is it? It's the number of pairs of vertex pairs and a time step A, so that vertices U and V have at least x many common neighbors during this interval, and U and V is active during this long interval. 2, ratio of this quantity 2, the total number of vertex time step pairs with at least x many common neighbors during this interval. So this was the so as you can see, again, the cumulative closure rate goes to 1 as the number of common neighbors increases. Okay, so what did we do? We defined C-closed graphs, proved a bunch of combinatorial results, algorithmic results. So as I said, the similar kind of bound hold for other dense graphs, called things like k-plexes and k-defective clicks, which are clicks modulo a few edges. So what are the next steps? The most important question, I would say, is how useful, so yes, these results show that, C closure number can be useful to design algorithms, but are they even more useful? What other problems are there for which you can design efficient algorithms using this structural parameter? This, to me, is the most important question. And of course, a more detailed empirical study, also, other similar results. All of these are open. So pick your favorite problem. What's the complexity of that problem on the class of temporal C-closed graphs? So that would be a really nice problem to work on. Okay, I'll stop here.
Thank you, Jayakrishnan. Any questions? I had a question about the plot, but you've shown it, so I'm good. But I can see that there's a couple of questions at least online. So let's start with Nidhi.
Yeah, hi, thanks for the presentation. So I observed that you have somehow coupled this closure number with the small scale graphs, right?
Mm-hmm.
So is there other sort of property that we can couple closure number with? Have you checked something else as well?
No, we haven't. So that's a very good thing to pursue. So, we were, trying to replicate the proof of the static C-close graph. And so we thought, oh, what property would be useful so that if we had that property, then we can replicate the arguments. So this is how we came up with this whole idea of instability. So yes, other properties would be really interesting to look at, or forget any other properties. Are there problems for which just C closed is enough to design good algorithms? This would be interesting.
Thank you.
Thank you. Victor? Or John? I don't know who's
Hi,
got the question.
John.
Yeah, hi. We're in the same office. So, hi, Jay. That's a
Hi.
nice talk. So Kitty and I had this paper on temporal cluster editing, where you try and take a graph and edit it into a bunch of maximal delta cliques that are suitably separated.
Mm-hmm.
Did you discuss this at all with Kitty? This could be a natural problem to parameterize by C and eta.
We had talked about this paper, but not in this context, actually. So we had talked about this when we were discussing what definition of temporal clique to use, because the definition is, if I remember correctly, is slightly different in that paper. You define a temporal clique to be a collection of edges, time edges, and rather than a set of vertices, I believe.
Okay, maybe I misunderstood. Okay, I had a vague idea, maybe for parameterization, where you could say that you in this setting where you're slowly varying and your C is small, you have not so many maximal cliques. And I was thinking these should be your somehow templates for what your cluster should be, and
so they could very well be related. So one thing I can tell you is about static C-close graphs. And the cluster editing problem, the cluster deletion problem on static graphs. So can you delete at most k edges so that the graph becomes a cluster graph? So for this problem, you can design a polynomial kernel using something from C-close graphs. So static C-close graphs have this nice property that there is a polynomial upper bound on the Ramsey number. So you can use that property to design a kernel for cluster deletion problem on static graphs. So this connection is there that I know of between cluster modification and C-closed. So this is a very good direction to pursue. Could be a natural thing to try.
Okay, but I guess Kitty. Well, I got the definition of the two cliques wrong, but I guess Kitty already knows this work.
I should hope so. Yeah.
Yeah. Okay. All right. Cheers. Thanks a lot.
Thank you.